In previous video, we saw the continuity equation, and then we talked about the momentum equation. And this is the momentum equation without the viscosity. Now we want to write these two equations in matrix form. But before doing that, we need to understand the number of unknowns. For example, in these two equations, the first unknown is rho, the second unknown is velocity u, the third unknown is pressure p. So we have actually three unknowns. Three unknowns. And how many equations we have? We have two equations. Two equations. And according to the theory, when we have more unknowns than number of equations, then you cannot I mean, this is inconsistent problem. We also know that from the linear algebra as well. So what we need one more equation so that the problem becomes consistent. So what should we do? First of all, we need to understand on which fluid we are working on. For example, which fluid? Is it a water? Is it a gas? Which fluid is this? In this case, the work we are doing, here we have gas that we are working on. Let's start from a simple fluid, which is a gas. It can be a water, but for water, the theory will be different. So if we have a gas, then it means that we can use some kind of relation. Since the density, if density is a constant, then it is for water. It is for water. So this is no more a unknown. But if density is a variable, then it is an unknown. It requires it needs a solution. We need to find a solution. So you know that if we have gas, then there is one famous law, which is not law, but we say that the equation of state, equation of state. So we can use that equation of state. But before working on equation of state, we actually find we put some assumptions. First assumption is we consider a gas is placed somewhere and it is adiabatic. It means that no heat transfer, no heat transfer. For in no heat transfer, let me just okay. For example, if we have a container and if some gas is over here, then it is just placed there without any heat transfer. No heat is provided externally. Another assumption that we want to make is the reversible process. It is not actually true assumption, but we assume that the process is reversible. When the process is reversible, it means that no energy is lost due to friction. And you know that whenever there is some movement, some transportation, energy is always lost during that process. So it means that it is not a reversible process. Okay. With these two assumptions, we want to write an equation, and the equation is P is equal to K hat rho gamma. So this is the equation. This is not exactly equation of state, which is written like this. You already know this equation. Probably you have studied this in chemistry or maybe in physics. But this equation is called polyatomic, I'm sorry, polytropic, should be polytropic equation of state. This equation is derived in thermodynamics by using equation of state, but it has some particular relation. K hat and gamma are constant. Gamma is famously known as Cp over Cv, and the K hat is just a constant. Okay, we will not talk about these since this is not a thermodynamics course. So we found an equation, and this equation is dependent on density. So we have three equations, one equation, two equation, and the third equation is here. So it means that now we can solve this problem. So if I just copy that equation over here, copy and I paste over here, since I want to change the equation. So here, if I just put, for example, if I put K hat rho gamma, this will be equal to 0. And simply, I would say that this is P, which is dependent on density, and this is equal to 0. Now you know that. Now we have two unknowns, in fact, three unknowns and three equations. So now this is consistent problem. This is now consistent equation. Okay, we found a way to solve the equation. And remember one thing over here, the P dash rho is greater than 0 for rho greater than 0. When you increase the pressure, it means that the density will also increase. So I want to write these two equations into a matrix form, and the matrix form will become, for example, here we have Q and this is rho U. So Q will become rho and rho U due to the first term, and then the flux will become, this is the flux, these are two terms, since these terms are inside the derivative, so these are the flux term. So I write the flux F, and you know that it is a function of Q. So Q is, what is Q over here? In this time the Q is rho and Q is rho U as well. So we have flux term over here rho U and rho U square plus P pressure, which is a function of rho. If I just want to write this in terms of Q, for example, if this is Q and I want to write this in terms of its components, Q1 is rho and Q2 is rho U. So how can I change the flux term accordingly? the flux term should be written in terms of Q1 and Q2. So this will be equal to f of q. So you see that this rho u is Q2. So we can write this as Q2. So formally we write it Q2. How can we get the rho u square from here, from these two terms? For example, here we have rho u square, so we can write it like this Q2 square. It means that we take a derivative, sorry, not a derivative, but power rho u square divided by, if I divide this by rho, then you will get rho u square. So it means that if I write Q2 whole square divided by Q1, then we will get rho u square. So this becomes Q1. Remember that this Q1, the power 1, this is not a power anyway. These are the components of Q. And Q should be a column vector. And plus, if I look into that, then there is a pressure P plus P, and since it is rho and rho is Q1, so we write it in Q1. So I write like this, plus P Q1, like that. So that's how we transform, not transform, but written this system of PDEs into the matrix form. So it will be written like this: partial q by partial t plus partial by partial x, and this is equal to f of q, which is equal to 0. And you know where we started our lecture. We started from these equations, which was advection equation when f of q was equal to u bar and maybe q, right? So that's how we write the matrix. You should remember these matrices form. We will talk about these matrices in future. Thank you for watching.